Hello guys, welcome back. We'll be continue to learn the deep learning, even though sometimes it won't return as much benefits. I mean, in a short of time, you cannot get anything from the machine learning. But in a long term, just think about it. When you can understand how humans think or how to create an intelligent creature, it will have a lot of fun. But it's a long way journey. You may or may not achieve this goal in the near future, like 3 years or 5 years, but it's a long-term process. You can take it as an habit. You can generally start to develop your interests on it. Maybe one day, suddenly, by accident, you happen to create a robot or creature that just have the intelligence of human being. That will be awesome. So that's it. Let's get started. The journey of learning. Neural learning about ages and corners. Intro to convolutional neural networks. In this chapter, we got two stuff to learn: reusing weights in multiple places, the convolutional layer. The polling operation used in convolutional neural networks is a big mistake, and the fact that it works so well is a disaster. Yeah, I couldn't understand what he was talking about. Reusing weights in multiple places. If you need to detect the same feature in multiple places, use the same weights. The greatest challenge in neural networks is that of overfitting. When a neural network memorizes a dataset instead of learning useful abstractions about that generalize to unseen data. In other words, the neural network learns to predict based on noise in the dataset, as opposed to relying on the fundamental signal. Overfitting is often caused by having more parameters than necessary to learn a specific dataset. In this case, the network has so many parameters that it can memorize every fine-grained detail in the training dataset, instead of learning high-level abstractions. When neural networks have lots of parameters but not very many training examples, overfitting is difficult to avoid. We covered this topic extensively in Chapter 8 when we looked at the regularization as a means of countering overfitting. But regularization isn't the only technique or even the most ideal technique to prevent overfitting. As I mentioned, overfitting is concerned with the ratio between the number of weights in the model and the number of data points it has to learn those weights. Thus, there's a better method to counter overfitting. When possible, it's preferable to use something loosely defined as structure. Structure is when you selectively choose to reuse weights for multiple purposes in a neural network, because we believe the same pattern needs to be detected in multiple places. As you say, this can significantly reduce overfitting and lead to much more accurate models, because it reduces the weight to data ratio. But whereas normally removing parameters makes the model less expressive, less able to learn patterns. If you are clever in where you reuse weights, the model can be equally expressive but more robust to overfitting. Perhaps surprisingly, this technique also tends to make the model smaller, because there are fewer actual parameters to store. The most famous and widely used structure in neural networks is called a convolution, and when used as a layer, it's called a convolutional layer. Yeah, we use that a lot, but I don't know why all those models that I made, it doesn't work. It doesn't work, even if I have added a lot of convolutional layer. When I say this, I mean the project that uses characters to play the Mario game. It is open sourced on my GitHub repository. You can check it out. Just Google InShellXO Play Mario GitHub and you'll find it. And it turns out it doesn't work. The convolutional layer. Lots of very small linear layers are reused in every position instead of a single big one. The core idea behind a convolutional layer is that instead of having a large, dense linear layer with a connection from every input to every output, you instead have lots of very small linear layers, usually with fewer than 25 inputs and a single output, which you use in every input position. Each mini layer is called a convolutional kernel, but it's really nothing more than a baby linear layer with a small number of inputs and a single output. You can see here's the inner picture of how convolution layer works. It just somehow found a way to convert a big picture, treat a big picture as instead of treat it in the pixel level, we group a few pixels as a whole part. Instead of processing those raw pixels, we process those sections. Shown here is a single 3x3 convolutional kernel. It will predict in its current location. Move one pixel to the right, then predict again. Move another pixel to the right, and so on. Once it has scanned all the way across an image, it will move down a single pixel and scan back to the left, repeating until it has made a prediction in every possible position within the image. The result will be a smaller square of kernel predictions, which are used as input to the next layer. Convolutional layers usually have many kernels. At the bottom right are 4 different convolutional kernels representing the same 8x8 image of a 2. Okay, here's the original image, the 2 image. And here you get the kernel stuff from the 2 image at the right picture. Each kernel results in a 6x6 position matrix. The result of the convolutional layer with 4 3x3 kernels is 4 6x6 prediction matrices. You can either sum these matrices element-wise, sum polling, taking the main element-wise main polling, or compute the element-wise maximum value, max polling. The last version turns out to be the most popular. For each position, look into each of the 4 kernels' output, find the max, and copy it into a final 6x6 matrix as pictured as at the upper right of this page. Upper right, okay? Here you can see that image. Yeah, it's very close to the 2 at the original image. There are a few things to notice in these figures. First, the bottom right kernel forward propagates a 1 only if it's focused on a horizontal line segment. The bottom left kernel forward propagates a 1 only if it's focused on a diagonal line pointing upward and to the right. Finally, the bottom right kernel didn't identify any patterns that it was trained to predict. As far as I say, from my opinion, I would say the 4 convolutional kernels in the right side of this page, looks the same. It's important to realize that this technique allows each kernel to learn a particular pattern and then search for the existence of that pattern somewhere in that image. A single small set of weights can train over a much larger set of training examples because even though the dataset hasn't changed, each mini kernel is forward propagated multiple times on multiple segments of data, thus changing the ratio of weights to data points on which those weights are being trained. This has a powerful impact on the network, drastically reducing its ability to overfit to training data and increasing its ability to generalize. A simple implementation in NumPy. Just think many linear layer and you already know what you need to know. Let's start with forward propagation. This method shows how to select a subregion in a bunch of images in NumPy. Note that it selects the same subregion for the entire bench. Okay. Now I can get that from here. Row from row 2, clone from clone 2. Yeah, the start point and the end point. After we get the subsection, we do a reshape. I don't know why he had to reshape that. I have no idea about that. Now let's see how this method is used. Because it selects a subsection of a bunch of input images, you need to call it multiple times on every location within that image, such a for loop looks something like this. Okay. It's just a process to get every subsection of that image. So we can do some process about the subsection, like determine whether we wanna return 1 or not. So we can return 1 or we can return 0. It depends on the subsection. In this code, layer 0 is a bunch of images, 28 times 28 in shape. The for loop iterates through every kernel rows times kernel clones subregion in the images and puts them into a list called selections. This list of sections is then concatenated and reshaped in a peculiar way. Pretend for now that each individual subregion is its own image. Thus, if you had a bunch size of 8 images and 100 subregions per image, you would pretend it was a bunch size of 800 smaller images. Forward propagating them through a linear layer with one output neuron is the same as predicting the linear layer over every subregion in every bench. I guess the meaning of that is to reduce the complexity of computation. If you instead forward propagate using a linear layer with n output neurons, it will generate the outputs that are the same as predicting n linear layers kernels in every input position of the image. You do this is because it makes the code much both simpler and faster. Okay, here's the code. First, we import the MNIST dataset. Then we define the activation function. Before we define the activation function, we did some work to get the training and testing dataset. Then we define the alpha iterations, those global variable or or hyperparameters. Then we define the getImage section function to do the convolutional job. Then we define the training process. I don't want to go to it too close because I don't think it has any meaning. It doesn't have it. You don't have to know those details because you could use the carrots, tf.carrots to do the same work with a simpler way. You don't have to write the code by yourself. As you can see, swapping out the first layer from the network in Chapter 9 with a convolutional layer gives another few percentage points in error reduction. Of course, as far as I say, image classification for a neural network, it is quite simple. But it's much more complicated when you want to put the deep learning to the reinforcement learning. For example, use it to play the Mario game. It's quite different. It's very hard to implement the deep learning algorithm to that game. It won't work as far as I say. I did that. I have spent a lot of time on that project. But if you use the deep learning with image classification, it's quite simple. It's quite simple. Most uses of convolutional layers stack multiple layers on top of each other, such that each convolutional layer treats the previous as an input image. Stacked convolutional layers are one of many developments that allowed for very deep neural networks, and by extension the popularization of the first deep learning. It can be overstressed that this invention was a landmark moment for the field. Without it, we might still be in the previous AI winter, even at the time of writing. AI winter. Summary. Reusing weights is one of the most important innovations in deep learning. Oh, that's how they said about the convolutional layer. They call it a reusing of weights. I didn't expect that. I used to think it as a transfer learning or something like that. I would think the reusing as a transfer learning. But it turns out it's not. The others think the convolutional layer as a method of reusing weights. Oh my god. I would think it as a reducing of weights. Convolutional neural networks are a more general development than you might realize. The notion of reusing weights to increase accuracy is hugely important and has an intuitive basis. Consider what you need to understand in order to detect that a cat is in an image. You first need to understand corners, then lines and edges, corners and small shapes, and eventually the combination of such lower level features that correspond to a cat. Presumably, neural networks also need to learn about these lower level features like lines and edges, and the intelligence for detecting lines and edges is learned in the weights. But if you reuse different weights to analyze different parts of an image, each section of weights has to independently learn what a line is. Why? Well, if one set of weights looking at one part of an image learns what a line is, there's no reason to think that another section of weights would somehow have the ability to use that information. It's in a different part of the network. Convolutions are about taking advantage of a property of learning. Occasionally, you need to use the same idea or piece of intelligence in multiple places, and if that's the case, you should attempt to use the same weights in those locations. This brings us to one of the most important ideas in this book. If you don't learn anything else, learn this: the structure tricks. When a neural network needs to use the same idea in multiple places, endeavor to use the same weights in both places. This will make those weights more intelligent by giving them more samples to learn, increasing generalization. Many of the biggest developments in deep learning over the past 5 years, some before, are iterations of this idea. Convolutions, recurrent neural networks, RNNs, word embeddings, and the recent published capsule network can all be viewed through this lens. When you know a network will need the same idea in multiple places, force it to use the same weights in those places. I fully accept that more deep learning discoveries will continue to be based on this idea because it's challenging to discover new, higher-level, abstract ideas that neural networks could use repeatedly throughout their architecture. Okay, that was right, because as a human being, our intelligence was not depend on the current. It depends on current situation and the memories from your past experience. Without the past experience, you are not intelligent. Okay, in the next chapter, we will talk about the neural networks that understand language. It's about the natural language processing, I guess. So I'll see you in the next video. Bye.